Welcome to Lecture 7.4, the wave equation. The goal of this lecture is to take the wave equation, which we saw at the end of last lecture, this thing right here, impose boundary and initial conditions on it, and solve it. So what we're going to do, we saw a preview of this at the end of last lecture, is we're going to have in this case we're going to have a string of, a wire of length pi, and we're going to be looking at waves, so things like this. And so we need to impose boundary conditions. U of xt is the displacement at position x and time t. So that's the vertical displacement. So again, if this is x, then this thing up here is this height is u of xt. So this little particle, this little piece is going to be going up and down like this, and every single point along this string is going to be going up and down as well. Okay, so the fact that these two endpoints are fixed endpoints, that means that u of 0 t and u of pi t equals 0 for all time t. And then the initial wave, the initial displacement is u of x0 equals h0 of x, and the initial velocity is u of x0, or ut of x0, and that's let's say h1 of x. And again, the velocity, that's how fast this thing is moving up or down rather than left or right, because it's with respect to t, not with respect to x. Okay, so here's our next example. Now I am continuing the numbering system from the first couple of lectures, where example 1 was the heat equation with type 1 boundary conditions, and example 2 was the heat equation with type 2 boundary conditions. So now we have the wave equation with type 1 boundary conditions, though these are the only ones that really make sense, because it doesn't make physical sense to have the rate of change be 0 if we have the wave equation. So we have a string of length pi, and the endpoints now are held fixed for all time t, and the string, the interior, can vibrate and move. So the initial wave is given by this parabola right here, and the initial velocity is 1. So that means that at every point here, it initially starts moving upwards with a velocity of 1. So it's like taking this point and throwing it upwards rather than just plucking the wave and dropping it and letting it go. Okay, so we will solve this like we did before. So we're going to assume that the solution separates. So there is a solution of the form, let's fix that. There's a solution of the form f of x times g of t. Now before I plug this in, we have to take derivatives. So u t equals f of x g double prime of t, and u x equals f double prime of x times g of t. Okay, so this is all we need to plug this thing back into here, but I also like to do my 0 boundary conditions. Let me actually remind you that these things are the boundary conditions, because that's when x is 0 and pi, and then this is an initial condition, as is this. So the 0 boundary conditions say that u of 0 t, that's f of 0 times g of t, is 0. And so of course this is a number times a function, which is 0, so that means that the number must be 0. So f of 0 equals 0. And then the other boundary condition says that is u of pi t is f of pi g of t. And if that equals 0, then again, this is a number times a function, and make sure that looks, this actually is a t rather than that's t. Yep. So that tells us that this number f of pi must be 0. So f of pi equals 0. Okay, so now we're ready to go. Let's plug this thing back into here. And notice we have two initial conditions. It's very possible that that one of these things could be equal to 0. So if that's the case, like if the initial velocity were equal to 0, then we could do the same thing here and conclude that we could conclude something about g. In this case, we could conclude that g prime of 0 was equal to 0, but it's not. But I think there will be homework problems where one of these things is 0, in which case I encourage you to do that before you plug this back in. Though you don't have to, you can always do it later. Okay, so let's plug back in. Okay, so UTT equals, that's this, equals c squared times this. So f g double prime equals c squared times f double prime g. Do the same thing I always do, which is divide both sides by c squared fg. C squared fg. And recall what cancels is, well, these f's cancel, these c squares cancel, and these g's cancel. And so what do we get? We get g double prime over c squared g equals f double prime over f equals lambda. Leave a little bit of room. So now we have two equations as before, so let's write those down. So we have g double prime equals c squared lambda g, and we have f double prime equals lambda f. And this comes with two boundary conditions up here. So we get f of 0 equals f of pi equals 0. So as before, this is the same boundary value problem. So we know the solution to this. This is a boundary value problem. We know that lambda equals negative n squared. Let's put that up here, negative n squared. And we know that fn of x equals sine of nx. So up here now, we have a different equation. Well, let's actually, this is equal to negative c squared n squared g. And that helps because now we know that this is harmonic motion, but this is sines and cosines rather than exponentials or sinus and coshs. So this is an ODE, and we know how to solve g double prime equals negative lambda, omega squared g, and now omega is just c times n. So this is so g n of t equals. Now I should probably use a and b here because I could have sines or cosines. So I have a general solution. So let me say an times cosine of c n times t plus bn times sine times c times n times t. Okay, so that's our solution for f, and this is our solution for g. Okay, so let's go down here and let's write what we know. So for each n equals, I'm going to start with 1 because again n equals 0, we get 0 for f. So for n equals, for these n, we have a solution of the form un of x and t, which is fn of x times gn of t, which is an cosine of cnt plus bn sine of cnt times, so that part's just the g. Now let's multiply by sine of nx. Okay, so our general solution is just the infinite sum of these. So I'm going to write that as the general solution is u of xt equals n equals 1 to infinity. Oh, I don't know if I let myself enough room. Let me give myself a little bit more room here. Otherwise, yeah. So u of xt is the sum from 1 to infinity of, I want to write sine first, I guess, just to be consistent with what we did last time. Sine of nx times an cosine. You know what? I'm going to use lowercase an just to match what we do for Fourier series. An cosine of cnt plus bn sine of cnt. And again, I'm running out of room. I'm going to try to squeeze it in here. Sine of cnt. Okay, and that is our general solution. I'm not going to write that out explicitly because I will do that on the next slide. But what's left now is to use these two initial conditions to tell us what an and bn have to be. Okay, so let's finish our example from the previous slide. We had the wave equation. Let me sketch what that looked like. So we had a bar of length pi, and we had a wave in that bar, and the initial velocity is it's going upwards at speed 1. And so what's going to happen is it's going to go back and forth forever. Waves don't dissipate like heat does. And so this is the general solution that we got, and now we have to use the initial conditions. So notice the difference between the wave and the heat equation is that the wave equation, you have sines and cosines here, which of course, as I said, we can write this as a single sinusoid that's shifted. Whereas in the heat equation, this thing, a function of t, was an exponential. An exponential is like a damper. It kills off each one of these sine waves. This thing does not. This thing oscillates forever. Waves propagate, heat dissipates. You can see it in the math. So let's plug in t equals 0. So we get u of x 0. And we get n equals 1 to infinity. And now what happens when we plug in 0? The sine goes away and we just have cosine. So in that case we have an times sine of nx. Looks kind of weird, doesn't it, to have an an with the sine of nx? Maybe more so for me than for you, but I think it's weird. So this is x times pi minus x. And remember what we had to do before? So we have to write this function as a sum of sine waves. So we have to compute the Fourier sine series of this. So that, if you recall from last time and from the section on Fourier cosine and sine series, I did this explicitly. That's this function. You'll be sick of this by the end of this class, of pi n cubed times sine of nx. So this an has to be equal to this if we want these things to be the same. So these things have to be the same. Okay, so now we have determined what an is. Next we have to determine what Bn is. And let me just mention that this thing here is the this is the Fourier sine series. Okay, so for Bn, we have to take the derivative and then plug in 0. So let's take the derivative of this thing here. So u, or the t derivative, ux of, or ut of x0 is the infinite sum, 1 to infinity. Now what do we get? So things pull, a c and an n pulls out of the cosine and the sine, and this one becomes negative. So we get negative an times c times n times sine of cnt plus bn times c times n times cosine of cnt. Again, the derivative of this, cn pulls out, this becomes cosine, and then this stays the way it is, times sine of nx. Okay, now let's plug in 0. Oh, I put in 0 here. Sorry, this should be t, not 0. Okay, so when you plug in 0, now we get n equals 1 to infinity of what happens. So this whole term goes away. All right, the sine of 0. This term sticks around, and this, of course, stays the same. So we get, actually, I didn't really need these parentheses. Oh well. Bn times c times n times cosine of 0 is 1 times sine of nx. And we have to set that equal to 1. How the heck are we going to do that? So we have the function, what does 1 look like? So at 0 to pi, we have the function 1. And we have to set that as the sum of sine waves. Well, we can do that. We take the odd extension, right, and take the Fourier sine series. And this is something that we have done before. So recall that the Fourier sine series of 1, you probably don't remember it off the top of your head, but we have definitely done this in lecture before. It is 2 times 1 minus negative 1 to the n all over n, say pi times n times sine of nx. And again, this is the, so this up here, this is the Fourier sine series, I probably should say, of x pi minus x. And this down here, this is the Fourier sine series of 1, which is a square wave. And of course this isn't a square wave, but we just need it to be 1 on this interval. So this is the Fourier sine series of the function 1, which of course is the square wave. Okay, so now it's tempting to say that Bn better be equal to this, but that's not correct. It's almost correct though. This coefficient of sine of nx, which is this whole thing, that has to be equal to this. So in other words, we get that Bn equals this whole thing divided by c times n. So Bn is 2 times 1 minus negative 1 to the n. Now let's fix that a little bit. Over c times pi times n squared. Okay, so now we have A. A is this. We have B, and now we are done. We just plug those back into here. So let's write this down here. U of x t is the infinite sum of n equals 1 to infinity of an, which is 4 times 1 minus negative 1 to the n over pi n cubed times, that should be a cosine, pardon me, cosine of cnt plus bn, which is 2 times 1 minus negative 1 to the n over c pi n squared times sine of cnt. So this whole thing has to be multiplied by sine of nx. And that is our particular solution to this boundary and initial value problem for the wave equation right here. And again, notice as if you take the limit as t goes to infinity of this, what happens? Well, this limit does not exist because these things are sine and cosine waves. They propagate. So this does not exist because waves, let me write that down, waves propagate and heat dissipates. So heat dissipates, we get e to the negative c squared n squared t. The fact that waves propagate, we see that in these, I'm just going to say cosine and sine terms, which do not die off. So these terms right here.